Okay guys, so I have to do this video submission because I was having some car issues this morning. I wasn't able to get to the school, but I chose to do my presentation over Tholins, these naturally forming polymers that we find in space. Now I have my laptop here with me so I can follow along the slideshow, and then I'll put the rest in later alongside this. This will be the Michael Cam. So let's talk about Tholins. We need to know where they come from. So first, this is Saturn, right here. This is Saturn, two pictures of Saturn, and then I have a photo of Saturn right next to its largest moon, Titan, relative in its orbit. Titan, if we move on to the next slide, Titan is a world rich in organic molecules, and its atmosphere contains these naturally forming plastics that we call tholins. You can see in these photos here that it is quite hazy. This oranger photo is the one that we got from the Voyager mission, and you can see a lot of those organic molecules in the atmosphere there. I mean, you wouldn't know that they're organic molecules just by looking at them, but now that we know, it makes sense that it's so hazy. You can see its size relative to Earth here, and then just more pictures of Titan. If we move to the next slide, I have a couple more beautiful photos of Titan. Now, Titan has a very interesting atmosphere. 95% methane, 5% nitrogen. I'm sorry, I always say that backwards. 95% nitrogen, 5% methane. Its atmosphere is much thicker than Earth's. Earth's is 100 kilometers. Titan's goes from 600 to 900 kilometers. That atmosphere is also much denser. It's about 1.5 bar to Earth's 1 bar, so that's about 1.5 times the pressure of Earth's atmosphere. And that whole atmosphere at the surface is negative 300 degrees Fahrenheit. So you have these very interesting conditions going on, and we see these volatile elements that we normally find on Earth as explosive or toxic gases existing as familiar, stable liquids on Titan. Because that's the really interesting thing about Titan, is that it has lakes and rivers of hydrocarbons, and it rains. The name Tholin comes from the Greek word for tholos, which is the word that they use for muddy orange thing. Carl Sagan coined this term to describe the muddy orange substance that they were finding in the upper atmosphere of Titan. He later, well, this was during the Voyager missions that they first did this. Later on, during the Cassini-Huygens mission, Carl Sagan worked with that team too, where they sent a probe to go down to the surface and investigate it. And we got a lot of data from that, as much as we could. The probe wasn't really designed to stay there for a long time, so it died pretty quickly. But the Cassini-Huygens spacecraft itself did a lot of science that it's honestly amazing that humans have been able to take the data that's there and come to the conclusions that we have. So let's actually move into what tholins are. We have our next slide. So whenever the Voyager probe entered the Saturnian system for the first time in the 70s, scientists used infrared spectroscopy to discover a whole suite of molecules like acetylene, ethane, propane, hydrogen, cyanide, carbon dioxide. And by using various spectroscopy instruments like the GCMS on the Cassini-Huygens probe, we were able to detect even more. We were able to detect bigger things like benzene and toluene. And we were also able to detect macromolecules, 8,000 daltons in size. And that's what we call tholins. These tholins, they form in the upper atmosphere of Titan due to energy bombardment. The methane and the nitrogen are bombarded either by UV radiation from the sun, electric radiation from Saturn's beast of a magnetosphere, or the cosmic background radiation that's kind of permeating space all the time. These sources of radiation radicalize the methane and the nitrogen into radical versions of themselves, which quickly polymerize in the upper atmosphere with other radicals. Now, it can go several interesting ways from here. They can polymerize up to a certain point, but because that radiation is still bombarding them, they just break apart and then start reforming at a different site. They can go through seasonal variations where there's periods of high energy bombardment, or a linking of multiple sources of energy bombardment that can really break up a lot of these polymers and start radical polymerization again. But this seemingly random cross-linking and the size of the macromolecules that we're seeing puts them on par with synthetic polymers like polyethylene terephthalate and polyethylene glycol. Okay, I cut right here. I'm back now. I wanted to circle back because I need to draw your attention to this photo here that we have in the background. These are pictures of lab-grown tholins that we've made. So this is what they look like. Now, the lab-grown ones aren't going to be exactly the same as the tholins in the atmosphere, but this is about what they should look like. Moving on to the next slide, we see sort of a column that shows the atmosphere of Titan. Now, whenever these molecules, these macromolecules, accumulate and grow to such great size, they eventually are suspended out of the atmosphere as an aerosol or a plastic dust, and that's one of the most amazing things that I've ever heard, is that plastic forms in the atmosphere of another world. Moving along here, I have another slide that shows sort of the difference between Earth's atmosphere and Titan's atmosphere. You can really see how much thicker it is here. You have that haze, that photochemical haze, rain, and that is moving on to our next interesting thing, which is the fact that Titan has lakes and rivers of hydrocarbons. So after the molecules become aerosol, they become the points of nucleation for Titan's unique methanological cycle. Just like Earth has a hydrological cycle, Titan has its own methanological cycle. Titan's climate is driven by its orbit around Saturn, which produces these 7-year seasonal variations, where you get north or winter in one hemisphere and summer in the other hemisphere, and then 7 years later it's the other way around. Now whenever winter comes, that's whenever it rains the most. And when it rains, this liquid ethane and methane, it doesn't just rain, it is a total monsoon. The suspended tholins are washed out of the sky and deposited onto the surface, where they then are able to interact further with those fluvial systems of flowing ethane and methane, which is amazing. Now, the really interesting question is what happens whenever the tholins hit the liquid. Because these lakes and rivers are made out of a nonpolar solvent, ethane and methane, and they're interacting with a nonpolar molecule, it may have some functional groups on it that have electronegativity and stuff like that, but for the most part, a long chain of carbon is nonpolar. So nonpolar, it's not going to dissolve it. Is that right? I feel like light dissolves light now that I'm thinking about it, but we can't get lost in the sauce on this one right now. Anyways, the point is the tholins do not easily dissolve in the actual hydrocarbon lakes. However, there is still a possibility for prebiotic chemistry to occur. If you look at this slide here, I have a photo of a normal cell wall versus the theoretical acetonitrile-based cell wall. So what happens is the ethane rain, whenever it comes down, the ethane comes out of the atmosphere first because it's heavier, denser. It's just weighs less than methane, so it's going to fall out first. When it does, you would think that it would sink to the bottom of the methane-ethane lake first too, but no, it actually forms a sort of oily film on the top of it. That oily film allows for the accumulation of acetonitrile-based tholins, or, no, I'm sorry, not acetonitrile-based tholins, that's later, acetonitriles. Now, whenever these seasonal events happen, these seasonal shifts happen, they can cause what we call lake flip events, where the methane and the ethane layer on top swap, and the ethane actually sinks down. This ethane layer has been saturated in these acetonitrile compounds, and so whenever they come down, it's theoretically possible that they could interact with that tholin, that organic plastic clay layer at the bottom of these hydrocarbon lakes, and actually give us the potential for interesting chemistry to still go on. forming an acetonitrile based cell wall, which would be absolutely amazing. This is completely different from any kind of prebiotic chemistry we've seen on Earth. And whenever we do put tholins in the presence of water, we do see that they make the building blocks of life very readily. However, there's not a lot of water on Titan. You do get it, there's not a lot of liquid water on Titan. There's a lot of ice on Titan. There's a lot of ice that's frozen for so hard and for so long, it's harder than granite. But that ice is all locked up in the crust. It's not until a meteor impact or some form of cryovolcanism happens that water actually can come into this system and interact with it. So while the potential is there, it's interesting to look at these possibilities for non-water-based prebiotic chemistry occurring. So moving on to our next slide, we have a picture here of Dragonfly. The Dragonfly program is just artist concept, but they actually are building the thing and it's going to ship soon. A major limitation in our current research is the lack of physical Tholin samples directly from Titan. We have to make all of our Tholin samples in the lab, and Tholins are kind of finicky. They don't like, it's not that they don't like, it's that they form different than what you want whenever you tweak the temperature, the quantities of nitrogen and methane, or use a different kind of energy input, such as a spark versus actual UV radiation. So it's really hard for us to make Tholins and to know that they're accurate to what we see on Titan. So what they're doing is they're sending a rotocraft. They're sending the Dragonfly probe in 2028, an actual flying probe that's going to go test, take samples from the lake, take samples from the soil and everything, and see what Tholins are, see if prebiotic chemistry is possible, if abiogenesis could occur, if we do find life or any kind of like fossil evidence or anything. Is that evidence for panspermia? The idea that, a meteor could hit Earth and spread life elsewhere, or vice versa. Lots of questions that we can answer from this. One of the most interesting questions is about Earth's abiogenesis. By looking at Titan, we sort of have this frozen planet-sized lab to examine the early Earth, and that's why we're doing it. That's why we're sending a probe. I mean, look at this photo here of this guy standing next to the probe. I mean, it's a lot bigger than you might think. Whenever I say we're sending a drone to Titan, you might think of a little flying around, but no, it's like a car-sized drone that's going to fly around and take samples of stuff. I mean, it's absolutely amazing. There's a potential for new kinds of medicine, new kinds of material science. Like, you guys would be really surprised to learn the effects that space science has on our everyday lives. So that's Tholins. Thank you guys so much. Appreciate it.